Welcome to another video. In this video, we're going to be talking about solving first-order linear differential equations. Now, a general first-order linear differential equation has the following form, where both dy over dx as well as y to the first power, and their coefficients happen to be just functions of x, and it's in this particular form. The first thing we like to do is we like to put this into standard form, which means to make the coefficient of dy dx equal to 1. So if we divide the general linear equation by a of x, then it will make that coefficient equal to 1, and we generally label the coefficient of y to be p of x, and then that function on the right to be q of x. And then we're going to need the ever-important integrating factor, which we label as mu, and it's equal to e to the integral of p of x dx. Later on in the video, I will show you where this formula comes from, but we're just going to use it to figure out why it's so important. So the idea is you take the standard form of the differential equation, and you multiply both sides by this integrating factor mu. Once we distribute mu through, the equation looks like this, and the idea then is to rewrite this left-hand side as the derivative of a product. And it turns out, with the choice of u that we have made, that e to the integral of p of x dx, it turns out that the left side will always be the derivative of the integrating factor times y. So this left side here will always turn into the derivative of mu times y, and that is how and why we have chosen mu in the way we've done so. So once you have the left side written as the derivative of a product, you're going to go ahead and solve for y. Well, how do we solve for y? Notice that y is being multiplied by mu, and then we're taking its derivative, so we're going to undo those. We're first going to integrate to get rid of that derivative, since the integral and the derivative cancel off, and the left side will just end up being mu times y, and we have some integral on the right-hand side. And remember, the goal is to solve for y. So how do we solve for y? We go ahead and we divide both sides by this integrating factor mu. So this is the formula for the solution to a first-order linear differential equation. However, you do not want to just memorize this formula. You want to go through the steps for figuring out where this solution came from in each of your examples. So what are the steps that you're going to follow to solve these first-order differential equations? Well, the first step is to put your differential equation into that standard form that we talked about. The second step is to find the integrating factor mu. The third step is to multiply through by that mu, and then to rewrite the left-hand side as the derivative of the product. And then finally, solve for y. So integrate and then divide by mu to both sides. So let's go through a couple of examples and show you how this technique works. So here we have a first-order linear differential equation. It is not in standard form, so our first step is to put it into standard form by dividing through by that x function in front of dy dx. And we can identify then that 3 over x is equal to p. Don't forget to also divide the right side by x, so x cubed became x squared. And now we need to find this integrating factor mu. Well, we're going to integrate 3 over x and then raise that to the e power. Well, the antiderivative of 3 over x is 3 natural log of x. Notice we're in the case where x is positive, so we don't necessarily need those absolute values, but we can use our rules of exponents to move that 3 inside the natural log, so it'd be x cubed, and then the e and the natural log cancel off, and giving us our integrating factor as x cubed. So that is our second step. The third step is to multiply the the standard form differential equation by x cubed. And notice I've multiplied every single term by x cubed. And this left side is the derivative of the product of mu times y, or x cubed times y. Let's check that real fast. Let's do the product rule here. So the product rule says leave the x cubed alone, then find the derivative of y. Well, that's where the dy dx comes from. Then you leave the y alone, and you find the derivative of x cubed. Well, the derivative of x cubed is 3x squared, and notice that the product of these two pieces here is indeed 3x squared. So yes, this left side is the derivative of this product. And again, this will always happen if you have calculated your mu correctly. Don't forget to also multiply the right side by that integrating factor, giving us x to the 5th. So our final step then is to solve for y. What do? We first integrate both sides because the integral and the derivative will cancel each other off on the left. So you'll just have x cubed times y on the left. And when you integrate x to the 5th, you get 1/6 x to the 6th plus c. And then finally, divide both sides by x cubed. And if we do a little bit of simplification, we can get our final answer as an explicit form and getting us 1/6 x to the 3rd plus a constant times x to the minus 3rd. There's our solution to the original first order linear differential equation. Now, let's take a look at another example, and I'm going to point something else out that you may or may not have recognized about the integrating factor. So first of all, this is a linear first order differential equation. It's already in standard form, so we don't need to do anything. The p of x is equal to 4. And the next step is to find mu, which is e to the integral of p of x dx. In this case, it's e to the integral of 4, which is 4x. And what you might have noticed here is that in both the previous example and this example, I didn't put a plus c when doing the integral as part of the integrating factor. And in fact, you don't need a plus c in that exponent, and I'll explain why later in the video, okay? So you do not need a plus c when you are integrating to find the integrating factor. We multiply through by the integrating factor. This is step 3. The left side is the derivative of the integrating factor times y. Let's check it. So the product rule says leave the e to the 4x alone, and then find the derivative of y, which is y prime. Plus, now you do it the other way around. Leave the y alone and find the derivative of e to the 4x. Well, that is e to the 4x times 4, exactly as we expect it to be. Don't forget to multiply the right side by e to the 4x. So we have this equation at the very bottom that we now need to solve for y. Well, we integrate both sides. The integral of the left, well, the integral and the derivative cancel each other off. So we just have e to the 4x times y. On this right-hand side, we can either use substitution, or maybe you know off the top of your head that the integral of e to the 4x is 1/4 e to the 4x. And when you multiply that 1/4 by 8, you get 2 e to the 4x. We do need a plus c here. Okay, this plus c, this integral is not part of the integrating factor calculation. So we do need the plus c here. And then we go ahead and make this answer explicit by solving for y, giving us our family of solutions. But don't forget, they were also given an initial condition, and we can use that to find the value of c. Well, I'm going to plug in 0 for x, I'm going to plug in 3 for y, and when I do so, I get this equation, which e to the 0 is always 1, so we just get c is equal to 1. And therefore, our final unique solution to this first order initial value problem is 2 plus e to the minus 4x. Okay, so there's two nice examples of solving first order linear differential equations. And really, again, all you're doing is you're solving these following these 4 steps each time. So please make sure that you are recognizing what the pattern happens to be. What are the steps for solving these first order linear differential equations? Now, there are 2 questions that I have left unanswered in this video so far, and one of them happens to be, where did that formula for mu even come from? And then I said that you don't need a plus c in the exponent when you're calculating the integrating factor, but why don't we need it? So let me explain both of those. First of all, where did the formula for mu end up coming from? Remember what the idea is. You take the standard form of the differential equation and you multiply the whole thing through by this function. You are trying to find some function where this left-hand side here is the derivative of some product. Okay, we want this left side to be the derivative of a product of 2 functions. And we don't know what this mu has to be in order to be this left side being the derivative of the product. Well, let me just go ahead and rewrite that equation on a new slide here. So we have the derivative of some product is equal to this right-hand side. And let me remind you of the product rule of f times g. It's f times g prime plus f prime times g. And the only way that these pieces on the right-hand side can match up with the product rule is if it goes this way. So first of all, g in purple here must match this function y so that g prime matches dy dx in green. Okay, so those have to match, which means that they have to be paired up this way. And therefore, that requires f to be the mu of x function. And then this part in blue, which is mu of x times p of x, that has to be f prime. This is the only way that you can match up each of these functions, f times g, with this expression here on the right-hand side. Which means that if f is equal to mu and g is equal to y, then the derivative of those two, the derivative of the product of those two has to look like this, which means that this mu of x times p of x, that has to be the derivative of mu prime. That's the important part here. If this ends up being the derivative of a product, then this piece here, mu of x times p of x, has to be equal to mu prime of x. So it turns out then that if mu prime is equal to mu times p of x, this is actually a separable differential equation. If I write this in our Leibniz notation for the derivative, and notice I've suppressed the mu of x, I've just written it as mu on the right-hand side, then I can separate the variables. I have 1 over mu d mu is equal to p of x dx. And what do we do with a separable differential equation once we have gone ahead and separated the variables? We integrate both sides. The integral on the left-hand side is just the natural log of the absolute value of u, and on the right-hand side, we just have the integral of p of x. And remember, our goal was to find what mu is. So if we raise both sides to the e power to solve for mu, then that left-hand side simplifies to be just mu, and it's equal to e to the integral of p of x dx, which is exactly the formula that I mentioned on one of the first slides of this video. So that's where this formula comes from. Again, you can go ahead and utilize this formula and understand where it ends up coming from. It's actually solving a separable differential equation in order to figure out what the formula for mu happens to be. The other unanswered question happens to be, why don't we need a plus c in the exponent of the integrating factor? Well, let's figure out what would happen if we did put a plus c there. So let's put some constant in that exponent. And then if we use our rules of exponents, when you have a sum in the exponent, then what you can do is e to the a plus b is actually a product of each of those exponentials. So I can write this as e to the integral of p of x dx times e to this constant that we've put here. All right, so I just used our rules of exponents to break up the sum in the exponent to be a product. And when we take this first order linear differential equation in standard form, remember what we do with it. We go ahead and multiply the whole equation through by mu. But if I do that, it looks like this. So if mu is equal to this piece up here, then when I multiply every single piece by it, take a look what happens. Every single piece has an e to the c in it, which is just a constant. We know it's not equal to 0. We can go ahead and cancel it, so it didn't matter what that c value was from the beginning. So no matter what c value you choose, it will end up canceling off at the very end, which is why it's not necessary to have that plus c in the exponent. So I hope this answers a couple of questions and gives a couple of nice examples about first order differential equations. I hope this video will help someone. I hope to see you in the next video.